So next up is one of the better cases, okay? My cable just got stuck in my shoe, fuck. Good morning, fellow mathematicians, welcome back to another video. I haven't done one of those quite some time, okay? Doing a math snack, a little math talk here yet again. Many of you pointed out that they are not really math snacks, they are more like math XXL meals because they are so long. This one is going to take quite a while too, but it's a really cool one. A few days ago, my boy Dylan Burger, the Hamburglar, okay, last time I fucked this joke up, posted this thing right here on Twitter, and at first it just looked really elementary because we have our parameterization up here as being the t, and we can simply solve. Okay, let's go through the process. We have x to the n plus mth power right here. Integrating that is going to result in, okay, from 0 to t, on 0 it's going to vanish, it's just a polynomial. So overall t to the n plus m plus 1th power over n plus m plus 1. And if we do the same thing here, okay, on the first one, on 0 is going to vanish all the time, and then t plugged in, so we are going to have t to the nth power, to the n plus 1th power over n plus 1, and also times t to the m plus 1th power over m plus 1. Okay, nothing special there. We can actually cancel out a 1 on both sides, a t and then to the n and mth power on both sides, leaving us with an expression for t. So if we just multiply both sides by n plus 1 times m plus 1, okay, so thus t is nothing but n plus 1 times m plus 1. Okay, I'm rushing through it because that's not even the real point of the video right here, okay, over n plus m plus 1. And for all t's of this form it does hold. We can actually simplify because this up here in the numerator is nothing other than n times m plus n plus m plus 1. Okay, meaning if we expand this out, we have n times m over this chunk plus n plus m plus 1 over the same thing, which is nothing but 1. So overall, this identity, this weird one up here, because multiplication is a billion, does hold for t's of the form 1 plus n times m over n plus m plus 1. Now we can get started with the main point of the video. For myself, if I see stuff like this, n and m's, I like to do a little bit of elementary number theory, okay? It's just in my blood. I just love to play around with cases a little bit. And do you know what would be interesting? To find positive integer solutions of t. So where t is element of the natural numbers without 0, so 1, 2, 3, 4, 5, blah blah blah, up until 317, because that's the biggest number, all Heil, Ababu. Okay, Ababu number, biggest number there is. Okay, so positive integer solutions for t. Also, I would like to place a few more restrictions on this whole thing, otherwise there are going to be a lot of infinitely many kind of trivial solutions. I want n and m to be also element of the same set. So 1, 2, 3, 4, 5 natural numbers without 0. Meaning, we want this to be element of n. N does form a group. No, it doesn't form a group under addition, but it is closed under addition. Let's put it like this. Meaning, if we have a natural number plus another natural number, both added together are going to be in n once again. 1 is a natural number, meaning in order for this whole sum to be in n once again, we need this part right here to be element of the natural numbers. And we are going to play around with this thing right here, considering all the cases. I made videos on that before. We can separate natural numbers into two different kinds, odd and even ones, okay? Even ones and odd ones. And that's what we are going to do. We are going to take a look at n being an odd number and then an even number, and then we have to do subcases where m is odd and m is even, okay? One cool thing is we can get rid of one case immediately because this thing right here is symmetric in n and m. So if we have n being odd and then taking a look at m being even, we don't need to do the same thing yet again with m being odd and n being even, okay? This is not something we need to do right here. So with all of that preliminary stuff out of the way, let us go ahead and get started. The very first case is a bit of a special one, okay, where n is equal to m. Can this be? Okay, is this something that does work out? N is equal to m. Oh, and one thing, I would like to find at least one solution to each case. This is the point of the video. I would like to find at least one positive integer solution of t for each and every case that we are doing here. Okay, if this case does work out even, okay? If n is equal to m, then we know that we have n squared over, in this case, 2n plus 1. And we want to see if this thing can be element of the positive integers without 0. Now, what does it mean for a fraction to be in n? Well, it does mean that the numerator needs to be at least greater or equal to our denominator, because, for example, imagine we would have 1/2. That's less than 1, okay? I hope you can see the problem. So this needs to be bigger than down here, okay? But we are not going to take a look at order relations exactly. What other does it mean for something to be out of n? It means that this fraction needs to be in n, okay? Might seem trivial now, but the numerator must be an integer, positive integer multiple of our denominator. Meaning, for example, if we have 4 over 2, this makes 2. Okay, I hope you can see the point right here. Meaning this statement in itself, and we are going to work with this extensively, is equivalent to saying n squared over 2n plus 1 must be equal to some natural number a. Okay, elementary number theory, here we go. A lot of case studies, a lot of handiwork to do. Now we can multiply both sides by 2n plus 1, it can be equal to 0. I hope you can see why this is the case. Thus, n squared is nothing other than 2 times a times n plus a. Now, I would like to do some simple manipulations. So what I thought when I first did that, well, it kind of looks like the binomial theorem already. So if we bring this to the other side, all that's missing is an a squared on both sides. Okay, I hope you can see this. So that's equivalent to saying we have n squared minus 2 times a times n plus a squared. We are going to add this on both sides, being equal to a squared plus a. Other than that, a squared plus a is nothing but a times a plus 1. Okay, we are going to need this in a second. Meaning overall, we can use the binomial theorem on here. That's equivalent to saying we have n minus a squared. This does look quite good, okay, being equal to a times a plus 1. And here comes one cool thing in. We can take the square root on both sides. It needs to be a positive. It needs to be a positive square root. Other than that, our n could be negative, which can't be the case because we want n and m to be out of the positive integers, okay? Taking the square root on both sides leaves us with the square root of a times this, but they are both positive by definition, meaning we can break up the third overall. I'm going through a lot of steps in one step, basically because I don't have too much time on my hands. Okay, I don't want this video to go on forever. Then we can add a on both sides, leaving us with an expression for our n. Now here comes one of the most interesting parts of this whole playthrough, okay, of this whole math let's play right here. N is out of the natural numbers, meaning natural numbers are closed under addition. A is out of natural numbers, okay, meaning square root of a times the square root of a plus 1 must be out of n. The natural numbers are also closed under multiplication, meaning square root of a must be element of n and square root of a plus 1 must be element of n. Okay? And we know that square root of a plus 1 must be element of n. By the same arguments as before, if something is out of n, it does mean that it must be equal to some number, for example p, and this be equal to some number s. And as a matter of fact, if you want to take the square root of a natural number and you want this thing to be in natural numbers yet again, it needs to be a perfect square. I hope this does make sense to you, okay? For example, square root of 9 is 3, that's natural number, cool. 9 is also natural number, but square root of 5, not Gucci, not even in Q, okay? Doesn't work, mate. Meaning we can square both sides, resulting in a being equal to p squared, and also we have a plus 1 being equal to s squared. And this was kind of a difficult part for me to actually filter out if this can work out or not. I was working with the difference of two consecutive perfect squares and shit like that, but I thought it might be easier to actually solve for a, okay? A is here s squared minus 1, we can set them equal. This implies that p squared is equal to s squared minus 1. And now here comes the really interesting part in. We can subtract p squared on both sides and add 1 on both sides, resulting in 1 being nothing but s squared minus p squared. And this is the difference of two squares, resulting in 1 being s minus p times s plus p. Let us divide both sides by s minus p. We don't want it to be equal to 0. Also meaning, so we don't want to be equal to 0, it does make sense. Other than that, we can divide by it. S must not be equal to p, okay? That's one of the conditions. That's equivalent to saying 1 over s minus p is nothing other than s plus p. Now, s and p, I'm mixing stuff up sometimes, are element of natural numbers, meaning their addition is also element of natural numbers. In order for this to be element of natural numbers, here comes the argument that I said before. We need the numerator to be greater or equal to this thing down here in the denominator. Meaning s minus p must be equal to 1. There is no other way this could work out. If it were 2, for example, it would be 1/2, not element of n. Doesn't work out. Meaning overall that we have s being equal to p plus 1. Now we can plug this stuff in, okay? Let me see. If we plug this in, okay, we know that this thing right here is 1, meaning we are going to get 2p. I'm going to put it here. So using this relationship, we have 1 being equal to 2p plus 1. We can subtract this on both sides, okay? Meaning overall, if we divide by 2, it's not equal to 0. P is equal to 0. But this is not something that works out because we wanted this to be element of natural numbers. We are running into a contradiction right here, okay? If we assume that n is equal to m, there is no way that we can have a solution in n. And let me tell you this is the only time in this whole case study where it does not work out. We can find a solution for this thing right here in n. This is something that does not work out. Okay, we have done the first one. I'm going to erase everything and then we are going to go ahead and do the next part, okay? So next up is one of the better cases where we can actually pretty easily find a solution. For this, I would like to take a look at just lower bounds, okay? So the next one comes quite natural in, okay? We can simply find infinitely many solutions for the next case. Spoiler alert, n odd and m even, or the other way around, it's symmetric, like I said. Okay, we want to find lower bounds for this to even hold, this relationship being equal to some a out of n. Okay, for this, like I said before, we wanted nm to be greater or equal to n plus m plus 1. Maybe you can already see where this is going. Now, how can we proceed from here? Well, we could do the brute force method and say, what about n being equal to 1? Okay, let's start off with that. Then we would have m over m plus 1, plus 2 even. M plus 2. This is even worse because there's no way our numerator could be greater than our denominator right here. Meaning this is never element of natural numbers. For the second case, we could take a look at the second natural number, n being equal to 2. Well, for that, we would get that 2 times m over m plus 3 could possibly be element of natural numbers. Okay, what about m being equal to 1? Well, that makes Doesn't work out, okay? We have talked about this before. N and M are symmetric, doesn't work out. What about M being equal to 2? Well, then we would have 4 over 5, okay, not element of N. But what about M being equal to 3? We would get that we have 2 times 3 over 3 plus 3. Which is 6 over 6, which is nothing other than 1. This does work out. We have found a solution, hooray. This is the point of the video. We want to find nice and sexy positive integer solutions. Okay, 1. This is good. We have found our first solution, meaning overall t is equal to 2 when we have n being equal to 2 and m being equal to 3. But there's something I thought to myself. Well, we have a pair of consecutive positive integers. 2 and 3. This is one possible pair. What about, for example, I don't know, 3 and 4? Or what about 4 and 5? And so on. Do they all work out? And I just thought, well, let's go through the abstract stuff, okay? We are going to set n being equal to n, okay? And we are going to take a look at the successor, m being equal to n plus 1. And this is really a cool case, because if you have n being even, then you have m being odd. That's one of the cases, okay? And the other way around too. What we have right here in this case is that we get, if we plug this into here, basically, we have n times n plus 1 over n plus 1 plus n plus 1. Meaning, this is going to give us 2 times the quantity of n plus 1, basically. So this is n times n plus 1 over 2 times n plus 1. Cancelling this out leaves us with n over 2. Remember, we want this relationship to be element of natural numbers. Meaning, if we divide a number by 2, it must be even for this to work. Okay? We can conclude that n is of the form 2 times k. It must be an even number. Meaning, if we take a look at consecutive positive integers, then n must be even and the successor thus must be odd. Meaning 2 and 3 does work as a pair. But 3 and 4 does not work as a pair, because if n were odd, this wouldn't work out. You could go the other way around and take a look at n being equal to 4 or n being equal to n and then m being equal to n minus 1, and you would arrive at the same thing, that n must thus be even. Meaning this doesn't work out, but 4 and 5 does work out, and 6 and 7 does work out, and 7 and 8 and 9, and so on. There are infinitely many pairs. We have infinitely many natural numbers, meaning we have infinitely many consecutive integers, and thus pairs of solutions. This gets rid of the case where we have one being odd and the other one being even. Now for the really hard part, okay? All of this was just child's play. We have found out a lot of stuff. Oh, and one thing I want you guys to notice, if we now have 4 and 5 right here, then our solution would be n over 2 to this whole thing, meaning we would have 2, meaning our t is thus 3, okay? So it just goes on, and it stacks by 1 each and every time. Now, we want n to be even this time, okay? This is one of the other cases, so 2 times k. And we want m to be also even. This is what we have now. So 2 times p. Leaving us overall, I'm doing this because it's a bit faster. If we take a look at that, we are going to get 4 times k times p over 2 times k plus 2 times p plus 1. And we want this to be element of natural numbers, meaning we want this to be equal to some a. Okay? And now we can go through this whole simplifying process yet again, multiplying both sides by this, leaving us with 4k times p being equal to 2 times a times k plus 2 times a times p plus a. Now, it doesn't quite matter, it's yet again symmetric in all of those parts, meaning let's just solve for p, for example. Let's filter out a value for p. Subtracting this on both sides, factoring out 4k and 2a, leaving us with, okay, we are having 2 times 2k plus a minus a, we are subtracting this on both sides, times p being equal to 2 times a times k plus a. Okay, if you wish, you can also factor out the a on here. Okay, I really don't care. This is what we have. We can divide both sides by this right here, leaving us with an expression for our p. Okay, I'm going to erase a bit of stuff right here. This is our p that we have at the moment. And now we need to do even more case studies. What about a being even and what about a being odd? Let us start off with a being odd. A being odd. Okay, this is something we can do if we have a being odd. This is going to result in something really nice. I'm going to put this into layman's terms. 2 times k plus 1 is always going to be an odd number. This is an odd number by definition. An odd number times an odd number is going to result in an odd number. So 5 times 5 makes 25. Okay, put this in numbers, it does work out for each and every n. So we have an odd number over 2 times some element of n. Okay, possibly under the condition that 2k is always greater, strictly greater than our a, meaning this down here is even. And this does not work out. Why does this pose a real problem? Well, we are going to make a quick proof by contradiction. Let's assume that this thing right here is indeed element of the positive integers. Overall, this does mean that this is equal to some, no, now we can't use a. Let's say we have 2k plus 1 over 2 times p. Okay, I thought someone was coming, I'm terribly sorry. If this were element of the natural numbers, we would say that this is equal to some, I don't know, s. Now multiplying both sides by this 2 times p, leaves us with 2 times k plus 1 being equal to 2 times s times p. S times p is out of n. We would have that an even number is equal to an odd number. It doesn't work in n, so 1 is not equal to 2. You just can't have this in n. I think I made a proof on that or something like that before. But this lets us run into a contradiction. Meaning overall that this case is not possible. A being odd is not a thing that could possibly work out. Meaning, at the moment, yeah, let us conclude this in the end, what this is going to say all about this. So many variables. Okay, now we are going to take a look at a being even. If a is even, that means it's of the form 2 times s is our a. Thus, we know that our p is 2 times k plus 1 times 2 times s over 2 times 2k minus 2s. 2 and 2 is going to cancel out. And this is something that does work out, okay? Depending on your s, yet again, it's kind of the same situation. But this is something that does work out indeed. Now, if we have s times 2k plus 1 over 2k minus 2s. Okay, you can factor out the 2 once again, it doesn't quite matter. We can actually find a solution to this whole thing. We want this to be element of n, yet again, meaning we want this thing right here to also be element of n. Now, we want the numerator to be greater or equal to our denominator. But here's one cool thing we can do. If we just want to search for a solution, we could also search for the minimal solution actually being possible. Why not let s be equal to 1? This leaves us overall with 2 times k plus 1 over 2k minus 2. Now, we can't have the denominator being equal to 0. That's not something we want. Meaning, if we were to set k being equal to 1, wouldn't work out 2 minus 2, nah, good. But if k were equal to 2, then we would have 4 plus 1 over 4 minus 2. This doesn't seem right. Why are you... What? We have 4 plus 1. Oh, yeah, this is the... Doesn't work out. Yeah, right. I totally forgot this. See, this is a math talk right here. If our s is odd, then we would have an odd number over an even number yet again, if we were to factor out the 2. Doesn't work out. So, even if we decompose a into something odd, even, then if we were to say that S is odd, this wouldn't work out either, meaning our A can, that's why I wanted to talk about this right here. I knew there was even a special subcase, sub-subcase. Yet again, we can't have A to be equal to 2 and 6 and after that 10, blah, blah, blah. Okay, this is not something that works. Now that we got rid of that, it's just by the same argumentation as up here. Let's set S being equal to 2, leaving us with, right, we are going to have 2 times this chunk over 4. Oh goodness, see, I'm still learning stuff. And now we want to find a minimum solution. K cannot be equal to 2, meaning we are going to set K to be equal to 3. Leaving us with, okay, this up here is going to give us 2 times 6 plus 1 over, and then this is going to be 6 minus 4 is 2. This and that is going to cancel out, leaving us with 7. This is the really cool thing. We reduce this to something that does work out. Okay, we have found out a pair, P and K. Okay, meaning our N is thus 2 times K, meaning 6, and our M is thus 2 times 7, which is 14. Leaving us with something abysmal. Okay, thus our T is going to result in 1 plus 6 times 14, give me a second for that, okay, and then we have over 21, okay, 6 plus 14 plus 1 is over 21, is 1 plus 6 times 14 is 48, over 21, results in 4, okay, 1 plus 4 is 5. Oh goodness, can't believe this worked out actually. That's, that's so cool. Okay, this has been a horrible case, and this is, I think, the only time where we have a sub case, okay? Now we are going to take a look at the thing when we have odd and odd, and then we are done with the video. And now for the last case, and then we are done, my boys and girls out there. So I've written everything out yet again, and I'm going to plug everything in. Let's do some mental arithmetic of those two being multiplied together, and then we are already good to go. Meaning we want this to be element of n under this condition, meaning we are going to get 4 times k times p plus 2p plus 2k plus 1 over those added together plus 1. So 1 plus, okay, this is going to give us 3 overall if we add those together, and then 2k plus 2 times p. And I would like to reduce this problem even more, because just like we did with here, we had this factor of 1 plus n plus m up here also in the numerator, and then we turn this into 1. We kind of have the same situation right here for this part, just with the 1 instead of the 3. So why not add a 2 to it and subtract it? This makes 3 in the natural numbers. Okay, successor of 2 is 3 and successor of 1 is 2, so double successor of 1 is 3. Okay, 1 plus 2 is 3. I hope you trust me on that. Meaning if we break this up, we are going to get a 1 and then plus 4kp minus 2. We have 2 as a factor. I'm factoring that out on purpose. So 2 times 2kp minus 1 over this whole chunk. So 3 plus 2k plus 2p. Why is this good? Well, we want this to be element of the positive integers without 0 yet again. Meaning closure under addition, it's enough to show that this is an n. Closure under multiplication, it's enough to show that this right here is an n. Meaning we can rewrite this as 2kp minus 1 over 3 plus 2k plus 2p to be equal to some a out of n. Now we can multiply stuff together. Yet again, if we bring this to the other side, that's equivalent to saying under condition that that is not equal to 0. It can be equal to 0, k and p are not equal to 0, and they can be the additive inverse of 3. Okay, with that out of the way, we have 2kp minus 1 being equal to 2 times a times k plus 2 times a times p plus 3 times a. We can add 1 on both sides, and we can solve for p once again. Okay, I hope you can see where this comes from, meaning we have 2 as a common factor, k minus a times p is equal to 2ak plus 3 times a plus 1. We can divide both sides by this term under the condition that it's not equal to 0, meaning k must be strictly greater than our a. And yeah, we are already at a point where we can do case analysis yet again. Maybe you can already see before, in the example before, we had even and even. And then if we choose A to be odd, we ran into a contradiction. Now you can go through this analogously. Now we have odd and odd. Why not say A is even? What is this going to result in? Well, then P is kind of the form. We have something even here. Something odd times even, 3 times 2, for example, is going to result in 6. This is something even. Even and even added together, 2 and 2 is going to be something even. So something of the form 2 times natural number plus 1 is going to be odd over 2 times the quantity out of natural numbers, even. And once again, contradiction. Okay, we got rid of that, and now for the case when A is odd. Meaning, what about A being equal to, let's go with S once again, 2S plus 1. Well, if we plug all of this in, we are going to get P is equal to, okay, let me see, I'm going to write everything out, 2 times 2S plus 1 times K plus 3 times 2S plus 1. Yeah, let's write everything out such that we don't do any mistakes. Plus 1 over 2 times K minus 2S minus 1. Okay, this is really good because you see, if we factor out everything up here in the numerator, we are going to get 2 times 2S plus 1 times K plus, okay, 6 times S, so 2 times 3 times S plus 3 plus 1 is going to be 4, 2 times 2. I'm going to put it like this, just because we can. Now you see we have factor of 2 everywhere. This is going to cancel out. We do not run into a contradiction right here, okay? This is really good. Meaning what we are going to be left with is the fraction 2S times K plus 3S plus 2 over K minus 1 minus 2 times S. And now we are going to look for a minimal solution yet again. Meaning K minus 1 must be strictly greater than 2 times S. Why not go for S being equal to 1, for example? Then we are going to get 2 times K plus K, so 3 times K overall, plus 3 plus 2 is going to be 5 over K minus 1 minus 2 is thus K minus 3. And now, choosing K to be strictly greater than 3, for example 4, that's the minimal solution possible, we are going to get over 1 in any case, and then 3 times 4 is 12 plus 5 is 17, meaning 17 is our minimal solution. Okay, so P is thus nothing but 17, meaning overall our M is 35. And our K was 4, so our N is thus nothing but 9. Ooh, we came really far with that, meaning overall, if we now solve for our T is going to be 1 plus 9 times 35, and I hope this is correct, seriously. Oh, that's a lot of work, I don't want to fuck this up. And then 1 plus 9 is going to give us 1 plus 9 is going to give us 10. Okay, 45, this is good. We are going to have a factor of 5 overall, so we are going to get rid of that. So this is 1 plus. Okay, 10 times 35 would be 315. 350, meaning minus 35 is going to give us 315, this time for reals, over 45. Okay, if we have 6 times 45, we are going to get 240 and then 270, so 7, right? This is 1 plus 7 is going to result in 8. We have found minimal solutions for each and every case right here. And I hope everything was correct. I don't know if there's a sub case yet again, but it does work out. If we, for example, choose this to be even, then we do not run into contradiction. This is even over something. Okay, yeah, right. No sub cases right here on this one. There was a really wired right. Okay, there was a lot of work and I hope you did enjoy this extremely long math snack this time. If you did, please like and subscribe and comment, and if you want to support the channel a bit more by those teachers, I create a support channel on Patreon. Up until next video, have a flammable day. See ya. Thanks Dylan Burger for this nice snack. Ciao.